Greetings, everyone. Welcome back into Calc 2 again. Time to go even deeper into power series that we've been talking about. Now let's mix up a little bit of calculus into the idea of power series. And by that I mean we're going to start trying derivatives and antiderivatives while we're in power series mode. Okay? And since the reason this is applicable is since we've added a variable that is continuous. Before, with just infinite series, the variable n was just a counter. It's not continuous. There's no way that we can do derivatives and antiderivatives with those kind of things because you need continuity. Okay? However, now that power series has introduced your x variable, x is something that's defined continuously on an interval, and therefore we can actually take derivatives and antiderivatives at those locations. Okay? So here's the idea. If I've got some power series that converges to some function, okay, so I've got a power series centered at c and it converges to a of x on some interval c minus r to c plus r. Okay? Now, whether or not the endpoints are included is another idea, okay? I didn't put the brackets on there because those are things that you have to check on an individual basis, okay? But let's say I have some interval. Then the power series is actually differentiable on that continuous interval. And the way that you perform it is what we call term by term differentiation. So if I take the derivative, d over dx, the derivative with respect to x, right, of the power series, then basically, even though n is a variable and c is a letter in there, I mean, those are all considered constant when looking down the barrel of x. X is the only variable that's being differentiated here. So it's a power rule. It's x to some number power, n. And the way we do derivatives with the power rule, right, is we just multiply by the n and do n minus 1. So n minus 1 is the derivative term by term. Each individual term is just a power rule, but I can do it generically on the nth term by dropping the n and subtracting 1 from the power. Okay? And on top of that, the interval doesn't change when you take the derivative. Okay? It's differentiable on the interval of convergence, and the interval of convergence of the new series that you've just changed it into, changed or created, whatever way you want to look at it. Okay, the interval of convergence is the same, but you have to recheck endpoints. Okay, notice I did not include the endpoints here, and that's because of the consequence in this calculation here is that you have to recheck endpoints. Okay, it kind of makes sense though, right? Remember, things aren't differentiable at endpoints a lot of times on intervals where you don't have something that's guaranteed to be in the domain on an endpoint, right? So when I take the derivative and get this new series, I've got to take the interval of convergence and recheck the endpoints to see if it still converges there or if it doesn't anymore, or even if it didn't before, it might now. It changes a lot of times when you take the derivative. Okay? So you need to recheck the endpoints every time you do a derivative if you're going to talk about the interval of convergence. Antiderivative is very similar. Okay? I can do the antiderivative on the continuous interval. Okay? And the interval of convergence stays the same. Okay? And you have to recheck the endpoints. That's all exactly the same idea between derivative or antiderivative. Performing the antiderivative, again, is also term by term, and it's x to some power n. I'm doing the antiderivative with respect to x, hence the dx. And so x to the n, I just do x to the n plus 1, divide by n plus 1. Okay, so it's just your plain ordinary power rules. And to be specific right here, this thing converges, okay, to the antiderivative of this. I'm sort of being a little bit lazy and sloppy with my terminology here. I know what you're thinking. Shouldn't there be a plus c? And yeah, you could put that if you want to, right? Technically, there should be a plus a constant here, right? Not to be confused with the c that's the center there. However, that's not really going to come up a lot with the stuff that we're doing because we're already adding up all of the individual terms. And then the thing that my series is going to add to is whatever the basic antiderivative would be with a plus zero. Okay? That's the way our infinite series are going to start out. And if you want to change them to something with another plus a constant, it's always easy to add that on if your application calls for it. Okay? So we need to think of it in the way that this right here converges to the antiderivative of whatever a is. And I'm using the integral symbol, like I said, in sort of a lazy way here. I'm just sort of glossing over it, okay? Just so that you can get the idea of what we're doing here, okay? So let's throw out a few examples here, okay? So let's try taking the derivative of this power series here, okay? So to take the derivative of this, I'm going to focus on the fact that I have x to the n plus 2 power there. And really, the derivative is independent of n because it's dx. So what's really happening is the derivative is skipping over everybody because it's not important, and it's really just applying to the x. Okay, and again, that's sort of lazy terminology, skipping over things, but it just doesn't apply to any of those other pieces. So the derivative of this I'm going to have the 1 over n squared plus 1 times n plus 2 times x to the n plus 1 power. Because what did I do? I took the power that was there, right? I dropped it and I subtracted 1. N plus 2 minus 1 is n plus 1. So I did a power rule there. Okay, so let's consolidate this a little bit. Whoops, wrong color. I now have the sum from n equals 0 to infinity of n plus 2 over n squared plus 1 x to the n plus 1. Okay? Now let's talk about interval of convergence for this guy. Right? Here, the interval of convergence is, I'm going to use the root test here. Okay? According to the root test, I can see that the nth root of this is going to tell me that x has to be in between 1 and negative 1, right? Because the x to the n there. And then the nth root of n squared plus 1 is just 1, so that doesn't actually contribute anything. However, if you test the endpoints right here, the endpoints, my interval of convergence, if I plug in 1, okay, I have 1 to any power is 1, and it gives me the summation of 1 over n squared, which I can compare to a p-series to show that it converges. Okay, so the interval of convergence at 1, right there, includes the 1. Same thing at negative 1. At negative 1, this becomes an alternating series, which makes it an even stronger convergence. It has absolute convergence for the alternating series at negative 1 there. Okay, so this one actually includes both of the endpoints. My interval of convergence here for the original series is negative 1 to 1. That's his interval of convergence. Now take a look at the derivative. It's going to be the same interval because, again, if I take the root test, right, the nth root of n plus 2 is 1, the nth root of n squared plus 1 is 1 as n goes to infinity, and the nth root of x to the n plus 1 still tells me that my x has to be in between 1 and negative 1. Okay? But now, when I test the endpoints, if I plug in 1, then 1 to any power is 1, and I'm left with the infinite sum of n plus 2 over n squared plus 1. And when you go to look for convergence of that, I can compare it to a series, but since I have n over n squared, that compares to 1 over n, which diverges. Okay? So that means I can't include the 1. When I put in negative 1, I get an alternating series, negative 1, and then this does pass the alternating series test. It's conditionally convergent there. So my interval of convergence here is negative 1 to 1, where it only includes the negative 1. So that was the point I was trying to make with you. It's going to be the same interval of convergence, all right? You can go through the whole test and see that it still remains the same. But the endpoints can change. It could go from not having either one to having both. It could go from having both to just having one, like it did here. You just have to test the endpoints every time you do a derivative or an antiderivative with these. Okay, let's do this one. The derivative of the sum from n equals 0 to infinity, x to the n over n factorial. Again, the n factorial is not affected by the derivative because it's not connected to an x. The summation is counting by n's, also not affected by x. X to the n is the thing that I'm actually taking the derivative of here. So what do I get? I get the summation, n equals 0 to infinity, right, of n times x to the n minus 1 over n factorial. Now, a lot of times what happens with these series when you take a derivative also is that you can actually lose a front term. By lose, I don't mean that it just disappears. I mean it'll zero out. What's going to happen when I plug in 0 here? Right? I'm going to get times 0, and it's going to zero out that first term. Also, here's another thing. If I simplify this, n divided by n factorial, okay, don't forget that n factorial, I can actually reduce this as n times n minus 1 times n minus 2, right? This goes all the way down to 2 times 1. So this is what n factorial is. So the n will actually reduce with the front guy of that, and it'll leave me with n minus 1 factorial. So I have 0 to infinity still, x to the n minus 1 over n minus 1 factorial. And then this is where it was actually important. Before I do this reduction, I should have also taken into account what I said a moment ago. The fact that if I plug in the 0, it zeroes out the front term. And here's why. Look at what's going to happen here. Can I do a negative 1 factorial? No. So actually, I should have fixed it. The n equals 0 term zeroes out and is gone. So it becomes n equals 1 to infinity because I just lost that front term. And now it makes sense, you see. 1 minus 1 is 0 factorial, and then I can do 1 minus 1 here. Also, here's another thing to consider. Once you've gotten to something that's simplified, if you don't like the way it's being left like this, you can shift your index. Okay? I know this isn't something we've talked about a lot, but you do need to know that this is possible to be done. What I do is I just pick another letter, not N, just something else like A or K or M or something. Okay? I'll use K. And here's what I do. I want to simplify this. I can say let K equal N minus 1. Okay? So then watch what happens to that. If I let K equal N minus 1, in this case, then I'll have X to the K over K factorial. Okay, now I haven't written anything on the sigma yet. Okay, all I've done is I've let K represent whatever N minus 1 is. Okay, so this is still going to go to infinity because you can't, take away the infinity. It's still, they're both going to be infinite. But k is whatever n is, but minus 1. So when n equals 1 is the first term, 1 minus 1, that means k is going to start at 0. Okay? Now the interval of convergence of this one was all real numbers. Okay? The IOC on this one was the entire number line. So of course that means the derivative one here also has the interval of convergence where x is all real numbers. No need to test the endpoints are infinite, okay? And here's another little jab that's going to throw you forward a little bit. Do you notice that I took a derivative of something and I actually ended up with the same thing back again? Sure, it's using k, but that's just a name. Do you notice that it's exactly the same structure? What else do you know that when you take a derivative, you get exactly the same answer back again? E to the x. So e to the x is the only thing that has that kind of property, right? And that's exactly true. This is the power series representation of the function e to the x power. We'll talk about that a lot more in the next couple of lectures as we go through Taylor and Maclaurin series, okay? But suffice it to say, you can see that this is one of the ways that gives you that little hint that this is that power series, okay? But a couple of good points here. When you take derivatives, you can lose endpoints, you can gain endpoints, whatever. Your interval of convergence itself doesn't change, but the endpoints can change. You can sometimes lose terms because they will zero out, and you definitely should reflect that in your pieces. Notice up here it didn't really happen because when n equals 0, right, I just had 1 originally, and then plugging in n equals 0 now, I still have a term at 2. So it didn't actually totally take that away for that one. Now if I keep taking derivatives on this one, right, and I eventually get down to n, that's when I would start losing the terms on it, right? Here, because n equals 0 and n was the piece I pulled down, that was when I lost one there. Okay, antiderivative works very similarly. Again, the antiderivative is only going to affect the x minus 2 portion. So I'm still going to have sum from n equals 0 to infinity. I'm still going to have the 3 to the n. I'm still going to have the 5. This now is going to be x minus 2 to the n plus 1. And then I have to divide by that new power, right? So I'm going to divide by n plus 1. So one way to consolidate this, 0 to infinity, I'll have 3 to the n over 5 times n plus 1, and then x minus 2 to the n plus 1. Okay? Notice the center doesn't change, right? Because either the derivative or the antiderivative is on the x. And when I do that, I can do a chain rule or a substitution, whatever you want to call it, and the inside derivative is still 1. Okay? So that's why we've written our centers the way we do with x minus or plus a number, because it actually doesn't affect the overall structure of our derivatives and integrals, right? We don't have to actually do anything extra there. Even if you did do a substitution, you'd see it really doesn't require that much of one. Okay? Now, did we lose any terms? If I plug in 0, no, I still get a good term there for 0. Okay? Doing the antiderivative there doesn't affect that. Let's look at the interval of convergence here. Okay? The interval of convergence for this guy, right, if I do the nth root, is going to tell me that 3 times absolute value of x minus 2 has to be less than 1, right? And then, of course, that tells me that x minus 2 has to be less than 1/3 as far as the absolute value is concerned. So then x minus 2 has to be in between 1/3 and negative 1/3. 2 is the same thing as 6/3. So then my interval of convergence here is where x is in between 5/3, right? Because that's 6 minus 1, and then 6 plus 1, 7/3. That's my interval right there. Now what about the endpoints, right? If I plug in on the endpoints here, this is actually, I don't even need the root test. I don't know why I said root test. This is all geometric series right here, because I can just do the 3, and this is all to the n power. Okay? Since this is all geometric, this one's not going to include the endpoints. This is my interval of convergence for the original series here. But what happens over here, right? The interval itself is going to be the same. Interval of convergence here is still going to be where x is a member of the 5/3 to 7/3. Okay? This one I do need something like a root test for, because I have the n plus 1 here now. Okay? But doing that causes me to solve this same inequality because of the major pieces here. And then the nth root of the n plus 1 just goes to 1. Okay? But I need to retest the endpoints. Should these be parentheses like they were before? These would be parentheses, right? Or can I actually include 1 now? Well, let's take a look. If I plug in, say, the 7/3, minus 2 is going to be 1/3, okay? And then the 1/3 times the 3 is 1. So all of this becomes 1 to the n, basically, okay? And I'm left with something on the order of 1 over n plus 1. Don't worry about the 5. It's an extra number I could factor out. And there's also an extra term in here with an extra 3 that I could factor out. That's fine. It would basically be 1 over n plus 1, which that's a harmonic series. So when I plug in 7/3, that diverges. Okay? But what about when I plug in 5/3? When I plug in 5/3, I get a negative value here, right? When I plug in that 5/3, I'm getting a negative 1/3 here. And when I multiply that times the 3, I'm getting a negative 1 to the n. It becomes alternating. If I plug in the 5/3 here, notice it becomes an alternating series. Here, let me show you what I mean. When x equals 5/3 to this one, okay, not the original one. When x is 5/3, I get 3 to the n times 1 over 3 to the n plus 1 over 5 times n plus 1. Okay, and that's 0 to infinity. Oh, sorry, it should be negative. Because 5/3 minus 2 is negative 1/3. Okay? Now, of course, the plus 1 is just an extra, and so is that 5. So really, I can just pull out a negative 1 over 15, because it'll be the 3 times the 5 in the denominators. That's an extra 1/3, and the extra 1/5, and an extra negative. And the rest of it will be 1 over 3 times 3. I'm going to get negative 1 to the n over n plus 1. Okay? So when x is 5/3, I have an alternating series that is conditionally convergent. By the alternating series test, this limit as n goes to infinity goes to 0. So this is conditionally convergent when it is alternating. Right? So therefore, I have gained this side right here. Okay? So in this case, I gained an endpoint on that one. Okay? So that's the point I was trying to make. I was trying to show you how you can gain and lose terms on your series, right? Sometimes, a lot of times, especially with derivatives, you'll lose something on your front end and you'll have to renumber. You don't have to re-index, but you do have to renumber appropriately if you do lose terms. and then your interval of convergence, the meat of it doesn't change, but you always have to re-inspect your endpoints unless it's, you know, the whole number line, of course, and you don't have endpoints. Okay? Being able to take the derivative and antiderivative of a power series opens up more avenues for creating power series of functions which were either too difficult or unavailable to us before. Here are 3 examples of some simple functions that can be found, their power series can be found using derivatives and antiderivatives. So right here, -6 over 1 plus 3x quantity squared. Okay, this really is mainly to show you in general, whenever you have something that kind of looks like one of those geometric types, right? Something with a 1 over 1 minus or 1 plus something, but then you've got this other exponent where the whole quantity of the denominator's there, right? So that throws out the geometric because of the quantity squared there. If it was just the x being squared, we could handle that with the geometric setup, but the whole thing being squared makes this unavailable for that. So in this case, what I can do is set this up like a derivative of some function that we already know the power series of. So notice that -6 over 1 plus 3x quantity squared is equal to the derivative with respect to x of 2 over 1 plus 3x. Because if I take the derivative of this, basically I have to use a -1 exponent and then a chain rule times 3. So the -1, the 3, and the 2 multiply to give me -6. And then this drops a power to -2 to get this. So if I take the derivative of this, I get the function that we're trying to find the power series of. But this right here, this rational function is something that I could easily find the power series centered at 0 for. So that's what I'm going to do. So then this is equal to derivative of the power series for this is going to be 0 to infinity. My first term is 2. And then this has got to be a negative right here in order for me to have the 1 minus the piece that I need. So then I'll have -3x to the n, like so. Which I can say then I would be taking the derivative of the sum n equals 0 to infinity of 2 times -3 to the n, x to the n. And I wanted to write it this way because I want to focus in on the x, right? I want to be able to do the derivative of the x piece of this. So now I do the derivative of that, and I end up with the sum from n equals 0 to infinity of 2 -3 to the n x to the n minus 1. Now remember what we said about derivative of these things before. Sometimes we lose a term, especially when I multiply by n. Notice if n equals 0, 0 times everything in the first term wipes everything out. So actually I'm going to lose that term, and I'm just going to start at n equals 1 now, right? And also that lines up in my exponents as well. 1 minus 1 gives me x to the 0, which is typically where we like our power series to start, with the x power of 0. With our power series should be starting with x to the 0 power. Okay, so now I've got a power series representation of the original function that we were interested in. Let's talk about interval of convergence. Okay, the interval of convergence of this guy right here is telling me that the absolute value of 3x has to be less than 1. Dividing by 3, notice the absolute value got rid of the negative there. So dividing by 3, it tells me that the absolute value of x has to be less than 1/3. So that means that x would have to be in between negative 1/3 and positive 1/3. Okay, so that's the interval of convergence for this. Okay, which means it's going to transfer to being the interval for the interval of convergence for this guy. Right? So far on my interval of convergence, I already know that x is going to be a member of the interval from negative 1/3 to positive 1/3. But since we took a derivative here, don't forget we have to recheck the endpoints, right? I'm going to have to recheck where these things are coming in at. And you know what? Matter of fact, I want to move this over a little bit to give myself some space here. Okay, so my interval of convergence, I'll go ahead and just write it right here. It's going to be from negative 1/3 to positive 1/3 like this. Okay, and now we just need to figure out to fill in the brackets or parentheses on these two here. So let's fill in. If I have negative 1/3 for my x, if x equals negative 1/3, then I will have the negative 1/3 to the n minus 1 power. And then I still have the negative 3 to the n. So I'll have the summation where I have 2, and I'll have negative 3 times negative 1/3 to the n, basically. And then what I'll do is times n, and then times negative 3. So you see what I did with the n minus 1? To make them match the powers, I pulled out another negative 3 from here, so that the negative 3 and the negative 1/3 that came from the x have the same n power. Now, right here, negative 3 times negative 1/3 is just 1 to the n power, which is just going to be 1. So I have the sum of negative 6n, basically. And n is going from 0 to infinity there. Okay? So therefore, this is going to diverge. Like, badly. Right? Because it's just n to the 1 power, and it's just going to keep growing. What about when x is positive 1/3? I think we're going to find a similar difficulty here. Right? A similar difficulty for us because when I plug in the 1/3, I'll have negative 3 times the 1/3 again to the n, and then n times 3. The 3 again, because I'm doing n minus 1 for when I plug in the 1/3 into x, so I'm balancing out to make it n, to make these two match. Negative 3 and 1/3 are going to give me negative 1. So I have 2 negative 1 to the n, and then actually it's 2 times 3, so it's 6, and then n, which is an alternating series. And by the alternating series test, I need to look at the limit as n goes to infinity, but that is going to go off to infinity, so this also diverges. Okay? So therefore, both of my endpoints on my interval of convergence here are not included as well for this one. Okay, so this is the power series representation for this, and you can re-index it and do different things like that. I mean, there's different things that you can do, but there's nothing wrong with leaving it in this format also. This is not a bad format to leave it in. Okay, so next, g of x equals ln of x. We're crossing out of what we've been talking about. A lot of power series has been with rational functions. We're crossing into more transcendental functions. You'll notice these last two are not related to polynomial and rational stuff whatsoever, except one way. I know that the derivative of ln x is 1 over x. So in our case, g prime right, the derivative of what we're interested in is a rational function. From here, what I'm going to notice is that I can now make the power series of this and then apply it with an antiderivative to give me the power series of the ln function. And that's really major because the ln of x is one of our big useful functions that comes up in a lot of different applications. So having a power series for ln gives us that first insight into maybe how we can start approximating a lot of our logarithm values. Okay, so here's what I'm going to do. I'm going to rewrite 1 over x as 1 over 1 plus x minus 1. Because to use the geometric, part of the rational thing, I need a 1 minus something over here, right? So that's what I'm going to do. I'm going to take this right here and I'm going to rewrite it. Okay? And then what's going to happen is then this, our derivative, g prime, can then be written as an infinite series, n equals 0 to infinity. And then what I've got is the negative x minus 1 there being raised to the n, like so. Okay, well then, just to write that another way, that's n equals 0 to infinity of negative 1 to the n times x minus 1 to the n. Okay, and then what's the interval of convergence on that guy? Well, my r is the x minus 1, remember? So then I have to have that piece right there, the x minus 1, the absolute value of the x minus 1 needs to be less than 1. Okay? So then this leads me to negative 1 is less than x minus 1 is less than 1. And then I add 1 everywhere and notice that I have a convergence interval between 0 and 2. Now that's the interval of convergence for this guy. That's my derivative function. Okay? So my ln, this guy, is going to be equivalent to the antiderivative of this. Okay? Now here's the thing. I'm saying that this is equal to, and I'm using the integral symbol, which technically we should have a plus, a constant at the end, plus c. And what I'm going to say is ln of x is a specific, not a generic antiderivative. It's whatever value it takes to cause the plus a constant to be 0. Okay? So when I do this antiderivative, I'm doing it of this series here. Negative 1 to the n, x minus 1 to the n, like so, dx. Okay, so then my ln of x is going to be equal to the sum n equals 0 to infinity of negative 1 to the n divided by n plus 1 times x minus 1 to the n plus 1. Okay, now again, there is a plus c after doing that antiderivative, but this is more like an initial value problem. I know specifically that I'm not just doing any antiderivative. My original function has already plus a constant where the constant is 0. I have the original function. Okay? I don't need a generic constant for this antiderivative. I already know the specific antiderivative I want, not the most generic one. So I'm not putting the plus c. I technically did, but then I'm saying that I know that my plus c is 0. All right, because I knew the initial function, the initial condition. That's why it's more like an initial value problem. Okay, so here is a power series representation for the ln of x. Okay, the interval of convergence for it is between 0 and 2 because taking the antiderivative doesn't change the interval of convergence. And then, of course, we would retest the endpoints. Trick question, though, can I do the ln of 0? Of course not. So it's going to diverge on that one. You can already guess that, right? My interval of convergence for this guy, x is a member of 0 to 2, and actually the 2 is going to be included. Let's take a look at that real quick. If I plug in 2 here, 2 minus 1 is 1, and 1 to any power, right, is done. That leaves me with negative 1 to the n over n plus 1, which is an alternating series whose limit goes to 0. Therefore, it passes the alternating series test. It is conditionally convergent, and it does actually converge at x equals 2. 0, of course, is not going to work. You'll notice right away that if I do that, the two alternatings will multiply out to just being 1, and I'll be left with 1 over n plus 1. But you should also expect the 0 to diverge. You can't do the ln of 0 anyway. Okay? So there's my interval of convergence for this power series right here. And if we ever wanted to actually, approximate a value of the ln of x, this isn't a bad way to start, right? You can actually plug in the first 5 or so terms of this and see where that leaves you with an approximation. It's an alternating series, so we can apply all of the rules that we had for approximating with alternating series back in that section. So keep that in mind whenever we come up to wanting to approximate one of these. Okay, arctangent of x. With arctangent of x, I'm going to treat it very much the same way as this other one. I'm going to say that dy dx is 1 over 1 plus x squared. The derivative of the arctangent function is 1 over 1 plus x squared. And I can then turn that into a power series directly. That power series is going to be from 0 to infinity of the negative 1 to the n, x to the 2n. Take a real close look, right? I have to do the double negative to make it the minus that I need for the geometric crossover. And then it's x squared to the n. So the negative 1 comes from the negative, and then the x squared is x to the 2n. All right, so this is a power series representation for the derivative of what I'm interested in, right? So therefore, my arctangent of x is going to be equal to the antiderivative of that power series dx, right? Okay, and then this tells me that arctangent of x is equal to the sum from n equals 0 to infinity. I have negative 1 to the n still. Now I'm going to do my power rule here, right? My power right now is 2n. So my new power is 2n plus 1, right? You add 1. And then whatever that new power is, you divide by it. So divide by 2n plus 1. So now I've got a power series representation for the inverse tangent function. It's a very, very potent power series, a widely used function that probably is very good to have as an approximation, right? Something that we use in a lot of different applications. Let's do the interval of convergence on him, right? Notice my original r up here is x squared, well, negative x squared. And then sort of the same idea here. I know that my x squared has to be less than 1 in size, which is basically telling me that my x has to be between negative 1 and 1. But remember, I need to test the endpoints because I did an antiderivative and the endpoints can change. The original function can't use the endpoints, but this one might. Let's check it and see. If I plug in 1 or negative 1, right? let's do that. When x equals negative 1, I get negative 1 to the 2n plus 1 there, right? Let's just look at that piece by itself. Negative 1 to the 2n plus 1. Well, 2n plus 1 is a guaranteed odd number, which means I'm going to have a negative 1 to an odd number. This is always going to be negative 1. In other words, it's just a number that I can factor out. So I'm going to get a series, negative 1 to the n plus 1 over 2n plus 1, n equals 0 to infinity, which is an alternating series with a limit of 0. So this converges by alternating series. Incidentally, the same thing happens when you plug in x equals 1, but to an even simpler degree, because 1 to any power is 1. So I actually end up with practically the same series with a slightly different exponent on the negative 1, which is also convergent by alternating series. Therefore, my interval of convergence here for the arctangent power series is where x is anything between negative 1 and 1 and including negative 1 and 1. Let's sneak in two more examples where I can use the calculus of power series to my advantage to help me create or find or calculate something. First, let's talk about another finding a power series of a complicated function. We definitely already have seen something how to do a power series with a logarithm. Now let's look at a power series of a logarithm that has something more complicated inside of it. In this case, 1 minus x squared. And this is going to bring together something from the last lecture as well. I'm going to break this thing apart into multiple series and then bring them back together with addition and try to use a pattern to create a very efficient power series for this function. Okay? So first, what I'll do with this is I'm going to split it by the logarithm rules. So the ln of 1 minus x squared is the same thing as the ln of 1 plus x times 1 minus x, just difference of squares there. And since it's a logarithm of a multiplication, I can take that and split it into the ln of 1 plus x plus the ln of 1 minus x. Okay, so I'm just using my logarithm properties here to do that. From here, though, I can actually say that each of these is a integral away, or rather an antiderivative away, of being something that would be easy to convert from a power series. Okay, so this is still equal to our function f right here. Okay, this is just another way of rewriting our function f here. And then from here, I'm going to say that this can be taking a derivative of this, right? F prime is going to be equal to the derivative of each of these. You know what? Let me line this up better. So f of x is equal to ln 1 plus x ln 1 minus x. Okay. Then from here, like I said, I'm going to take the derivative, f prime. The derivative of this is just 1 over 1 plus x. And the derivative here is going to be minus 1 over 1 minus x. Right? Because the derivative of the ln, 1 over whatever's inside. This one happened to have a chain rule inside derivative of negative 1. All right. So then from here, both of these can be written as power series. So I have f prime is then equal to the sum from n equals 0 to infinity. I'll need to bring up a double negative here. So that's going to be negative 1 to the n, x to the n for this one, minus the sum from n equals 0 to infinity of just your ordinary x to the n. Right? That's that one. Merge these together, and I get a power series n equals 0 to infinity of negative 1 to the n minus 1 times x to the n. Okay, all I did was I factored out the x to the n that they had in common there. Now that's f prime. Okay? The original function f is then going to be the antiderivative of this. So integral n equals 0 to infinity, bracket negative 1 to the n minus 1 x to the n dx. Once I perform this antiderivative, again, technically there should be a plus c, but don't forget, we know that our plus c is 0 because we already know what the original function is here. So I'm not worried about a plus c for this. I'm just going to integrate by doing the n plus 1 power here. So I'll have the sum from n equals 0 to infinity of negative 1 to the n minus 1 all over n plus 1 times x to the n plus 1 power. So now I've got a power series which represents the original function. Okay? And then what's the interval of convergence on this guy? Well, back from the original one here, we had to see that the absolute value of x had to be less than 1 for this guy. And same thing here, the absolute value of x had to be less than 1 for that guy. So my interval of convergence is going to be between negative 1 and 1. Right? From this right here, we can see that already. My interval of convergence is where x is going to be an element between negative 1 and 1. Okay? I'm actually going to go ahead and say that that has to be the limit, and no matter what you do to check these endpoints, it's not going to come out. And I'm going to show you another way that I know this in a minute, but just take a look at the original function. The domain of this original function, his actual domain right here, is none other than x is an element from negative 1 to 1. Because if you plug in negative 1 or 1, 1 minus 1 is going to be 0, and I can't do the ln of 0. Anything larger than that, I would be doing the ln of a negative number, which is complex, literally with the imaginary values, complex values. Okay? So ironically, our interval of convergence here is actually the entire domain of the function. It's very handy in that case, right? Okay, so I've got an interval of convergence, and I have a series right here. Although that's kind of a weird looking series, though, with the negative 1 to the n minus 1. Since they're just simple ones like this, you'd be thinking to yourself, why can't I just combine those and get negative 2? But it doesn't work that way, right? Because sometimes negative 1 to the n is 1, and sometimes it's negative 1. It depends on if n is even or odd. Okay? Well, here's the thing that draws you in to be more interested in this one. In the times where n is even, I'm going to get 1 minus 1, which is 0, which is going to wipe out that whole term. And in the other times, I'll get negative 1 here, minus 1, which is negative 2. So it's like I have all of the numbers n equals 0 to infinity accounted for, but literally half of them are going to zero out. So I could actually make this series more efficient by just looking at a pattern real quick. Okay, so this is definitely one representation of the power series. Okay, we can leave it like that if we wanted to, but you would probably also be pleased with this other one. So write out the first few terms. Okay, this is equal to, when n equals 0, I have -1 to the 0, right, which is 1. -1, which is 0, okay? And then n plus 1 is going to be 1. I've got 0 over 1, and then that's going to be 0 plus 1, which is going to be x. Okay? Plus, if I let n be 1, then -1 to the 1 is going to be -1 minus 1 is -2 over 1 plus 1 is 2. Okay? Then I'll have x to the 1 plus 1, which is 2, so x squared. Okay? Plus, you'll notice the next n is 3. It'll be odd. I'll have -1. I'll have 1. Not odd. N is 2. N is even. So I'll have 1 minus 1, which is 0. I'm just going to start putting 0, and then that's going to be my x cubed, technically. All right. Plus, the -1 minus 1 again. I'll have -2 again. But now n is up to 3. So 3 plus 1 is 4. And I'll have x to the 4. The next one's going to be 0, x to the 5, and then the next one after that will be -2 over 6, x to the 6th. Hopefully you're seeing the pattern now, right? All of the odd powers of x to the 1, x to the 3, x to the 5, are completely wiped out, right? These are gone. Every other term happens to zero out. And each and every one of the even terms has a -2, and then the power and the denominator are the same number, 4, 4, 6, 6, right? Naturally, because they're both n plus 1. We can make a new pattern out of this. This is actually equal to the sum from k equals, and I'm picking a different letter so you don't get it confused with that one, okay? But where k is going to be equal to 2, you see, okay, from 2 to infinity. I'm sorry, not to 1, right? Because this will be my n equals 1 term. You'll see what I mean. Where it's -2, because each one of them has that, times x to the 2n over 2n. Okay, so think about that. 2n is always an even number. That's why I picked it. So 1 times 2 gives me 2, right? When k is 2, 2 times 2 is going to give me 4. When k is 3, 2 times 3 is going to give me 6. So it's going to count all of the even powers. Okay? So this is actually another way of representing that exact same power series, just in a more concise way, a more efficient way of doing it. And basically all I did was I'm just wiping out the half of the terms that are zeroed. Okay? Now these two series are equivalent. They are actually equal to each other. Okay? Because power series are unique. Right? Once you find a power series for a function, there's always only that one power series. And the only time it would look different is if you change the center. Okay? So these two are equivalent. They are equal. They are both equal to that original function when they converge, right, on the interval of convergence. Okay? So real quick, just go take a look at what this looks like in GeoGebra so that you can see the entire function is approximated by either this power series or this power series on its entire domain. Here's that function, y equals ln of 1 minus x squared. Notice it is indeed trapped in between -1 and 1. And then I've got the two different power series here that both supposedly were equivalent and represented it. As you can see, even when n equals 1,
This guy already has a couple of terms ready to go. And technically this guy is the same thing because this one is going to be zeroed out. Okay, these are actually going to be the same series, but you don't actually notice it right away. But since I've trimmed the fat basically on this second one here, it's going to converge to the curve faster. So watch, I have this one on, and you can see as I let n increase, it does in fact fit to the curve. Okay, same thing with the other one here. It does actually, but you notice it goes a lot quicker. And it fits right up on top of that curve. Right, you can see that it is indeed a very, very good approximation of that curve. Okay, now look at both of them together. You can't see them you see the red dots and the green dots. They're right up on top of each other at first. Okay, now we jump one time and you see the green one has already started to converge, right, where the other one has only added a zero term anyway. So then as we go, it's like the green one stays ahead of it for a while. But they are both equivalent because they both converge to this function on that on the interval from -1 to 1.
Now, another application here where I have just a series. That's not even a power series, right? But they want us to find the value that it converges to. First of all, how do we know it converges, right? Well, just look at the balance. I have an exponential function, really powerful, over just a simple polynomial. Comparison test, ratio and root test, definitely you would have a 1/4 to the 5th situation. It's a very, very, very strong convergent series here, okay? Or a ratio test, you get the same result where the denominator is much more powerful there. Among many other, the other tests that we have. But you can see that this one definitely converges, plus they give you the hint, hey, it converges, right? But it's not a power series, so why are we talking about it right now? Well, look at the series. It's not in any of the formats totally that would allow me to just calculate the answer. It's not fully geometric because to be fully geometric, it can't have a multiplication by the n there. The n plus 1 kind of throws that out. It's not telescoping, and it's not any of the other little nitpicky little series that I can just try to add up. However, I can convert this into a power series by saying that this is one value, okay? So in other words, imagine on all of these other power series, whenever we've talked about interval of convergence, we're saying that it works for all of these different x values. Well, what if this is just one of those x values where some power series is convergent? So this could be like one value of a power series. Okay, and that's actually really what a power series is useful for, because it's supposed to be a generic function. A power series is the function form, and this would just be one of the plugins, right? This would be like f of 10 or f of -2 or something like that. Whereas, over here you have like your f of x. So that's the way you should be looking at this. If it's asking us to do that, it's a crazy looking series. Well, maybe I can turn this into a power series, and then maybe I can try to manipulate that power series into something I recognize, which I can then turn into a function and possibly calculate this value. And that's actually exactly what we're going to do. So let's do some manipulation here. I'm going to take this and I'm going to say that it's equal to the sum from n equals 0 to infinity. I'm going to take the n plus 1 and sort of separate it out here. And then what I've got is 1/4 to the 5 n power times 1/4 to the -3 power. Okay? That's what I'm doing. I'm just splitting up this complicated exponent here so that I can make it look more like a power series that's useful, right? Just something to the n. Okay? And then this 1/4 to the -3, that's just a multiplied number. I can crank that out to the front. Okay, so here we go. This is going to be equal to this 1 over 4 to the negative 3, that's 64 times the sum n equals 0 to infinity n plus 1. Now right here, instead of 4 to the 5n, okay, I'm going to write this as 1 over 4 to the 5th to the n, so that I can have one chunk to the n power and make it look more like that geometric structure. Now, of course, it's not totally geometric, right, because of the multiplied n plus 1, but we're working there. We're getting there slowly, okay? And the way this works is, 1 to any power is still 1. So technically, this is 1 to the n and 4 to the 5th to the n. So now think of this more like what I was saying a minute ago. What if this is just one instance, one plug-in of a more generic power series? Okay? So what I'm going to say is that this is actually equal to 64 times the sum n equals 0 to infinity n plus 1 times x to the n, evaluated, so I'll just say when x is equal to 1 over 4 to the 5th. Okay? 4 to the 5th is 1024, so I'll just put that. 1 over 1024. Okay? Now, I'm writing the words right here so that you'll get used to seeing what I'm doing. But if you think back and you remember some of the terminology that you had from integrals and derivatives, remember we have those ways of writing brackets or straight bars that can have a value that's supposed to be plugged in. So instead of writing the when x is this, instead what I'll be saying is that it's this evaluated when x is equal to 1 over 1024. Ugh, that's atrocious. 1 over 1024. So these are equal. This is just this power series evaluated when x is that value. Okay? If you prefer the brackets, sometimes that's kind of like whenever you're doing an integral and you have the low and the high, you can do that too. This is equal to that power series evaluated at that x value. That's just not the way I was doing it. I was just doing it with the straight bar, which is indicative of some derivative values too. Okay, but look really, really closely. If I were to integrate this, right, wouldn't the n plus 1 power be the next power up? And then I would have to divide by n plus 1. So right here, this, think of it in reverse, okay? I'm using the integral to understand what this is equal to. This is actually equal to the derivative of, this is equal to 64 times the derivative of, now what is this the derivative of? The sum from n equals 0 to infinity of x to the n plus 1, evaluated when x is 1 over 1024. Think about it. Work in reverse. If I take the derivative of this, remember the n plus 1 drops, and the n plus 1 minus 1 is n. So I can say that this is the derivative of that. And now look at it. It's just x to a power. That's all it is. Just x to a power means it's something that I can write using that geometric bridge, that power series back into a rational function. Okay, now it is x to the n plus 1, right? So what I need to do is separate off that extra x value. So I have 64 times the derivative of x times the sum from n equals 0 to infinity of x to the n. Like that. Evaluated when x is 1 over 1024. That's sort of something that's just hovering over it the whole time. All of this only holds at this one point. Okay, but that's the point we're interested in anyway. So now what series is does this turn into for a rational function? That means I have 64 times the derivative of x over 1 minus x, evaluated when x is 1 over 1024. Because this x right here would technically be my a value, my beginning value, and then x right here is my r, because it's to the n. So I have a over 1 minus r. Okay, so then now that I've sort of gotten over that bridge, like I built it up, got the series, and then I jumped over the bridge into being a rational function. Now I let it all collapse back down. Actually perform the calculus that you see here. Take the derivative of this function, plug in the value, is something that we can easily do, right? This derivative is a quotient rule. So I'm going to have 64 times low d high, right? So that's 1 minus x times 1 minus high d low. So that ends up being plus x over square of below. 1 minus x quantity squared. Okay, evaluated at x is equal to 1 over 1024. We're almost there. Notice in the numerator, minus x plus x is gone. So I have 1 over 1 minus x squared. Okay? So altogether, this is 64 over 1 minus x quantity squared, like that. Okay? Oh, you know what? Actually, there's an easier way to look at this. Let me show you another way of looking at this. This could be 64 times 1 over 1 minus x squared. Because if this is 1, right, 1 squared is still 1. And this is going to be easier to plug this value in. Because that's where we're at now. I'm going to take the value and I'm going to plug it in. So I've got 64 times 1 over 1 minus 1 over 1024, all squared. If I multiply everything by 1024, I get 1024 over 1024 minus 1, and that's all squared. So that's 64 times 1024 over 1023 quantity squared. And if you punch that up in your calc, right, save yourself a few minutes on that one, it ends up being 671,088.64 over 104.6529, which is approximately 64.12518,334. And there's the value that this series converges to. Okay? So even though it didn't start out as a power series, if you think of it as one function value, one plug-in of a power series, all you need to do then is turn it into something that I could treat like that. Like I could say, oh, this is where the x could go, and I just let x be that value for the moment, right? So let x take that spot, and then treat it like a function for the rest of the way. And then do whatever manipulations you think you need to do. In this case, I was able to use the derivative / antiderivative rules to help me out with this. Okay? So I hope this lecture has helped you understand the connection now more between calculus and the actual infinite series that we're going to be studying. At this point, you're now ready to get that final topic. The next lecture is going to be on Taylor and Maclaurin series and Taylor and Maclaurin polynomials, which is the more generic version of being able to turn functions into power series. Okay?